So I'm going to talk about single-shot error correction. So first of all, what is single-shot error correction? So it's an idea for how to perform error correction when you can't trust your measurements because they're noisy. So it's an idea that performs error correction without having to repeat the measurements over and over again. So this term single-shot was actually proposed by Hector. And why would you care about single-shot error correction? Well, to me, there are two main reasons. One is that because you're not having to repeat these measurements over and over and over, it's faster. So normally in error correction, you would have to repeat d times to do it fault tolerantly. So you have a kind of time saving. But the other reason is that it's more reliable in some sense. So, don't know what's going on there. It's more reliable in some sense, in that if you have time-correlated noise, or if you have some fabrication faults, then single-shot error-correcting codes will also be able to tolerate this kind of noise, where standard error-correcting codes won't be able to. So this was, again, also proposed by Hector at QIP. Oh, I think I figured out that backwards is forwards and forwards is backwards now. So there are lots of examples of codes that we know that have single-shot error correction capabilities, but most of the codes that have been proposed until recently have all been kinds of topological codes. So we've got 3D gauge color codes, 4D toric codes, and such what. These are all very nice codes, but they do have a bit of a disadvantage, which is that topological codes are constrained by trade-off bounds. So if you've got parameters n, k, and d, so these tell you how many physical qubits you have, how many logical qubits you have, and what the distance of the code is, then there are trade-offs between these parameters that you have to pay in order to have a topological code. So the kind of question that I want to ask here today is, what are all of the single-shot codes that we could conceivably think of? So this is kind of the question that I would like to answer. We don't quite get there, but I try and get as far towards answering this question as I possibly can. And the reason why I care about trying to understand all of the single-shot codes that there might possibly be is that there will be many codes that aren't constrained by these trade-off bounds, and so these might have better parameters n, k, and d, and be more efficient. Okay, so what's the key result that I'm presenting here today? So the bigger result, if by bigger you mean it took more pages to prove, is that for any classical code, if you give me any classical code, then I can put it into a recipe which uses something called the homological product. And out of this, I'll get a quantum code that has single-shot error correction. So for any classical code, I can use it to construct a quantum code that can perform single-shot error correction. Furthermore, if the original classical code is LDPC, then the resulting quantum code is also LDPC. So LDPC means low density parity check. So this means that the stabilizers that you're measuring, the checks that you're measuring to see if there's noise in your system, only affect a constant number of qubits. So this is kind of the big result, and then there's also a few more smaller results that I'm going to show you that to me just kind of helped my understanding about what single-shot error correction is. Okay, so let's recap kind of what just standard error correction is. So in standard error correction, so let's fix our error model. So we've got some number of measurement errors which are faulty and report the wrong answer, and we've got some number of Pauli errors. So let's say x is the number of measurement errors, and y is the number of single qubit errors that you've got. So the standard notion of error correction is that if I don't have any measurement errors, so this instance, x is equal to 0, and y is less than half the code distance, then we're going to be able to correct things perfectly. That's kind of the most basic notion of quantum error correction. So when you correct things perfectly, what this means is that there's no error after you've performed the correction. There's no residual error left over. So in single-shot error correction, we can kind of modify this definition and say that x and y obey some upper bounds. They're smaller than something, much like they're on the left-hand side, but now the upper bound on x can be non-trivial. Okay? So I'm going to be deliberately vague so I don't get into technicalities about what this upper bound actually is. Okay? So if we satisfy this criteria, and then we have a promise that there's a decoder, and that after we've used this decoder, the residual error on the system obeys some upper bound, so the error is less than or equal to f of x, so less than some function of the number of measurement errors that we had, then we say we performed single-shot error correction in some sense. Okay? So how good this is depends on what this function f is. Okay? This kind of definition on the right-hand side could include many instances of terrible single-shot error correction, where, for instance, this function is the exponential function. So let's say what we mean by good single-shot error correction. I find it really hard to define a good notion of single-shot error correction for a single code. So let's define it for a whole code family. Okay? So we take a code family, and we say that it's a good single-shot code family if these upper bounds that we had on x and y, the number of errors, grows with the number of qubits that we've got. But this function f, which tells us how large the error is that's left over, doesn't change as we go through the code family. And furthermore, it's a polynomial, so we're not allowing ridiculous kind of exponential functions. It's a nice, smooth polynomial. So if those criteria are satisfied, we say the code family is a good single-shot code family. So let's kind of go through a very, very simple example. The simplest example is actually a classical example. It's the 2D Ising model. So in the 2D Ising model, really what you've got is a repetition code. But there's some redundancy in the checks. You've got more checks that you're measuring than you really need to measure. So here, the bits are the squares, and the checks are the circles. So whenever I've got an edge between a circle and a line, that's telling you to measure the parity of all of the bits that are connected to that particular check. Okay? So this, for instance, is telling you to measure the parity of the joining two bits. Okay, so if you have a physical error, so if one of these bits is flipped, then what you find is that some of the checks are violated. You get -1 outcomes when you should have had +1 outcomes. So if you look at this pattern, what you see is that for any one of these loops, there's always an even number of -1s present. So this means that there's some extra structure, and that's what I've labeled here with this diamond shape. So these diamonds, we're going to use them throughout the talk. We're calling these meta checks. They're checks on the checks. So if you look carefully, what you can see is that for every single one of these diamonds, it's connected to an even number of -1 locations. Okay? So this is telling you that the parities here that you measure, they should, assuming that the error was generated by a physical error, all satisfy this meta check criteria. But let's say that it wasn't created by some actual physical error. There was some mixture of physical errors and measurement errors. So let's say that this measurement that we perform here should have reported a -1 outcome, but in fact, it reports a +1 outcome. Then what we see is that two of these meta checks can flag that up. Okay? So the meta checks are just classical post-processing that you perform on the measurements that you've performed, and they can kind of detect where measurement errors have occurred. So this kind of suggests a two-stage approach to decoding these kinds of codes. So in the first stage, you just try to correct the measurement errors. So what you do is you try to find the lowest weight or the smallest number of measurements that you have to flip the sign of to get a situation whereby all of the meta checks are satisfied. And then you take this repaired syndrome and you perform kind of more standard error correction. You look for the smallest weight physical error such that it gives you that repaired syndrome. So in this kind of two-stage setup that we've got here, if there was one physical error and one measurement error, you would say, well, the measurement error is definitely here because that's the lowest weight possible answer. And therefore, I guess that there's also an X error here. But you could get exactly the same observed signature from a different configuration. Say that there was no physical error, but there were 3 measurement errors. Then, by following a two-stage decoder, you would flip this bit when in fact it didn't need to be flipped. And so what this means is that you performed your error correction hoping to have removed all of the error in the system, but in fact there's going to be a 1 qubit error, so there's going to be some amount of residual error. But it's only 1 qubit, so it's not that bad. It's a low weight error. And in fact, you can see that the error in the Ising model is very, very constrained. There's this kind of area law, which I'm going to call more a soundness property of the code. So here I've kind of highlighted in red the bits that are flipped, and the boundary of this region are the syndromes that you have, or the measurement checks that are violated. And so for the Ising model, there are 2 different configurations that lead to the same syndrome. But for the lower weight one of these 2 solutions, the low weight solution, what you see is that there's a relationship between the area of this region and the boundary. So the boundary tells you how many checks are violated, and the area tells you how many bits are flipped. So you end up with a relationship between X, the number of, the weight of the syndrome, and the weight of the error. And in fact, this relationship is through a function which is quadratic. So that's a kind of topological example of a code which has this nice area property and nice soundness condition, which we're going to see on the next slide is related to single-shot error correction. But I want to talk about non-topological codes. So let's just kind of state what this soundness property is algebraically. So we say a code is TF sound if the weight for all syndromes that pass all of the meta checks, if the weight is equal to X, and that's less than some constant T, then there exists a Pauli correction, which is going to be, there exists at least one Pauli correction, which has a weight which is less than f of x. Okay? So again, for this first definition, T and f could be anything. So it could be something completely useless. We want to define what good soundness is. So a family of codes with good soundness is going to be a family where each element of the family is TF sound, where T grows with the size of the grows with the number of qubits, but this function f is exactly the same across all elements of the family, and it's a polynomial. Okay, so for the 2-bit Ising model that we had on the previous slide, this f of x was just a quadratic function, and t, I didn't show you what it was, but it was basically the size of the lattice. So it's going to grow as you increase the size of the lattice. So then the kind of first result, which is just really working through how the two-stage decoder works, is that if you give me a family of codes with good soundness, then you're going to end up with a family of codes that has good single-shot error correction. So this soundness condition that I've kind of stated just algebraically tells you a sufficient condition for being able to perform single-shot error correction. So some of you might be thinking, okay, it's a sufficient condition, but is it really a necessary condition? And I'll come back to that question on my last slide. Okay, so before we carry on talking about good single-shot error correction, we should probably also comment on what bad single-shot error correction is, or what bad soundness is. So in the toric code, if we have a string of errors like this, then we'll have a syndrome just at the end of the string. So what this means is that there are error configurations where the syndrome weight is just equal to 2, but the size of the error that leads to that syndrome, or even the smallest error that could possibly give that syndrome, is unbounded in size. It grows and grows and grows as you go to bigger lattice sizes. So there's no function f, which is a polynomial, that covers all of the toric codes. So this is not a family of good single-shot codes. Okay. So now we're going to cover a few kind of mini results that, at least to me, give me an idea of what this soundness notion is that is a sufficient condition for single-shot error correction. So first of all, we saw that good soundness entails good single-shot error correction. The next result is that it's related to something which lots of people have studied called a macroscopic energy barrier. So the second result just tells us that if we have a family of codes with good soundness, and it satisfies this LDPC condition. So remember, that's that all of the checks, all of the stabilizers that you measure of the code act on no more than a constant number of qubits. Okay, so you have those two conditions, and you also have that the distance of the code grows with the number of qubits. This entails a macroscopic energy barrier. So somehow soundness is very similar to something that many of you would have encountered anyway, the macroscopic energy barrier. So just to recap, I won't give you the proof, but I'll kind of recap what a macroscopic energy barrier is. It's just that if we have two code words inside the code and we try to go from one to the other, so two orthogonal code words, and we go from one code word to the other code word via a kind of walk. And in each step of the walk, we just apply a Pauli error, a local Pauli error on the system. Then for each step of that walk, we can associate an energy which is equal to the number of checks that are violated by the code. Then we say the energy barrier is the minimum possible energy price we can pay to go from one code word to an orthogonal code word. And we say the energy barrier is macroscopic if for a family of codes, the energy barrier grows with the number of qubits, at least as fast as n to some power. Okay? So a similar result was proved by Aronov and Eldar in their study of the PCP theorem, but they had a stronger notion of soundness than we have in this work. So I've kind of had to come up with another proof of this. So directly from this second mini result, we get another one. This is really just a corollary of the second result combined with the Bravi-Tohal result. So what Bravi and Tohal tell us is that if you give me a family of 2D topological codes with a distance grows with the number of qubits, then this can't possibly have a macroscopic energy barrier. And because it can't have a macroscopic energy barrier, it also can't have good soundness. So this result just follows immediately from that combined with Brabito-Hall. Okay? So the last kind of mini result that I want to tell you about might look a bit strange compared to the three above it. So this is telling us that for all codes, there exists a choice of checks such that they have good soundness. Okay, so this should look strange because I've been kind of sloppy up until this point. So up until this point, I've been conflating a code with the stabilizers that you measure on that code. But for any given code, there's lots of different choices of checks or stabilizers that you can measure on it. So all of these statements above are kind of presupposing a fixed notion of the checks or stabilizers that you're measuring. And in the last point, I'm just saying that if you give me a code and some set of checks and allow me to change the set of checks or stabilizers such that they still generate the whole code stabilizer, then I'll always be able to find such a choice such that it has good soundness. So this does not contradict the above results, and I'll show you why on the next slide. So I'll just kind of give you a little sketch of this result, of how the proof works. So the idea is you choose some set of generators for the code, and then you bring them into some diagonalized form that looks a lot like the canonical form for graph states. So the idea is that you can always bring it into a form that's kind of diagonalized. Up and down are like upside down to me on this controller. Yeah, you can kind of bring it into this diagonalized form where there are x's along this diagonal, and for any particular qubit, if there isn't an x, then there's either z or the identity. So you have this for the first number of qubits, which is equal to the number of stabilizers you have, and for the rest of the qubits down here, you don't care. So this is, you can always achieve this form up to local Cliffords just by kind of multiplying the stabilizers together and applying some local Cliffords. So what you can see here is that there's a local Pauli operator, say Z, acting on the jth qubit that anti-commutes with the jth stabilizer, but with none of the other ones. So what this means is that if I have one of my stabilizers violated, then I can correct this with a single qubit Pauli flip. If I have X of my stabilizers violated, then I can correct it by a weight X stabilizer, a weight X Pauli correction. So what this means is that this code has a soundness property which is f of x is equal to x. That's much better than the quadratic one that we saw for the Ising model, and in fact, a little bit of thinking can tell you that this is the best kind of soundness property you could ever possibly hope for. So we have this kind of bizarre situation, which is that it's actually really, really easy to come up with codes that have single-shot error correction against adversarial noise. That's maybe something that I didn't emphasize enough earlier. So against adversarial noise, any code can be made to have some kind of single-shot error correction property, but in the process of doing so, you destroy any of the other nice properties it might have had. If it was a 2D topological code, it's not a 2D topological code anymore. If it had some LDPC code properties, it might not have them anymore. So the challenge really is to try and come up with codes that are both LDPC and have this good soundness property. So this brings us to the last part of the talk, where I'm going to tell you about this kind of more bigger technical result, where we use the homological product to construct codes that have this good soundness property and which can also often be LDPC. So what we're going to use is the homological product. So for the simplest example of the homological product, you might also call it the hypergraph product. And in fact, Tillich and Seymour were the first ones to propose using the hypergraph product. So the hypergraph product, we can understand it as a graph product between two graphs. So here we've got two different graphs representing two different classical codes. So any classical code I can always describe by a graph that tells me how to measure different parities of different kind of classical bits. So let's just recap. Each square is a bit, and each circle is a parity check. And for every edge between a circle and a bit, we're saying measure the parity of all of the bits connected to that particular check. Okay? So these are two different repetition codes of different length, just as a simple example where they're not exactly the same thing. So the way the graph product works is you take many copies of these codes, and then you superimpose the two graphs on top of each other. So before I had two different graphs that had two different types of vertex each. So on the superimposed graph, I'm now going to have four different types of vertex. So the next thing we do is a bit of coarse graining. We say that two of these vertex are in fact the same kind of vertex. So if I had a square overlaid with a square or a circle overlaid with a circle, I'm just going to call that a simple plain square. And then I can identify these three different types of vertex with different types of thing. So the squares are qubits and the circles are again checks, but now I've given two different colors of checks, where the colors tell me if it's a Z check or an X check. So you can kind of see that this is maybe a quantum code, but there's one thing that we haven't checked, which is that the Z checks and the X checks actually commute with each other. So in a sense, that's the important thing of the hypergraph or the homological products, is that they always give you this property. Given any pair of initial classical codes. So many of you who have maybe thought about quantum error correction have come across the CSS construction, and it's important to contrast the two methods here. So for the CSS construction, you can take two classical codes and you can make a quantum code, but for the construction to work, for it to give you a code where the Z and the X checks commute, what you need is that the two classical codes sit dual to each other. And that's actually a very, very strong constraint, and it means that you can't use some of the most efficient classical codes in your code constructions. So if you want a really, really efficient code, you don't really efficient quantum code, you don't really want these kinds of duality constraints on your classical codes that you're using. And that's really the beauty of the hypergraph product. So I want to give you a bit more of an idea for why the hypergraph product gives you this commutativity property. And it's because it doesn't just build a bigger graph, it builds a graph which has a special property. And this property is that the graph describes what you would call in topology a chain complex. So I'm just going to give you the definition of a chain complex in this kind of graphical language. And it's that, so say we start off with a bipartite graph, then we can define a binary matrix that is really just the adjacency matrix between the two different sets of vertices that we've got. Okay, so there's a 1 if the two vertices are connected. Now let's look at a tripartite graph. Not just any tripartite graph, but a tripartite graph where vertices can only be connected if they sit in adjacent layers. So you can see here that I've got 3 layers, and the top layer is not connected to the bottom layer, but the first and second layer are connected, and the second and third layer are connected. So I can describe this graph by a series of adjacency matrices. I have a first adjacency matrix, delta 0, which describes the adjacency between this set of vertices and this set, and another adjacency matrix, delta 1, that tells me about the adjacency between this set of vertices and this set of vertices. Okay? So you can keep on iterating this definition and having more and more of these delta j's. And we call this a chain complex if for any consecutive pair of these delta j's, you find that when you multiply them together, addition modulo 2, you get the 0 matrix. So this might seem like a slightly random condition. The reason for it is that these ideas come from topology theory, where these operations represent boundary maps. And this condition is often stated as the boundary of a boundary is empty. So if you ever heard that condition before but never really knew what it was, it's referring to this kind of algebraic condition on graphs or chain complexes. Okay, so if you've got a graph that is a chain complex and it has 3 or more of these levels, we can identify one level with qubits, one level with X checks, and one level with Z checks. And then for the X and Z checks, we have to define some kind of parity check matrix that tells us on which bits they operate, on which qubits they operate. So for, let's say, the X checks, we just associate that with one of the boundary maps. And then for HZ, we take a different boundary map, the next one down, but we transpose it. So what you need in order for the X and Z checks to commute with each other is that HX times HZ transposed is equal to the 0 matrix. This is telling you that every possible pair of stabilizers actually commutes. Okay, so if I just plug in these choices of delta that I've given you here, I see that this transpose cancels this transpose, and I'm just left with delta j times delta j minus 1. And if this is indeed a chain complex, then this is equal to the all 0 matrix. So if we have a more complicated chain complex, I can also do something else. So if I've got something with 5 levels, then I've got enough structure now to also define the meta checks. So the checks on the X checks, and also the Z meta checks, which are checks on the Z checks. So I can define these, again, using these boundary maps that we've got from the chain complex. But you can't just define any old graph and hope that it's actually a meta check. The meta check actually has to be a valid one. It has to represent some actual redundancy in the code. So if you've got a bunch of stabilizers in the code and you believe that the parity of all of the outcomes of these should be equal to +1 when multiplied together, another way of saying that is that these Pauli operators, when multiplied together, should be equal to the identity. Okay? And that's obviously not always going to be the case if I just multiply together some random Pauli operators. But that condition is satisfied whenever this matrix times this matrix is actually equal to 0. So what this tells us is that if we've got a chain complex with 5 or more levels, then we've got enough structure to define these meta checks in a way that's valid. Okay, so that brings us to the double homological product. So we saw that the homological product applied once to a pair of classical codes gave us something with 3 levels. How am I doing? Gave us something with 3 levels. So in the double homological product, we just apply this procedure twice. And we end up with something that actually has 5 levels of structure. So this gives us all we need for a quantum code with meta checks. So here's some information that was kind of proven previously or recently by other people. So these are just how the parameters of the quantum code relate to the parameters of the classical code. So there's some simple relations that are easy to read off for n and k. But we also have this nice result that was proven very recently by Zheng and Priadko that tells us the distance of the quantum code is equal to d squared, when previously the best that was known was just that it was bigger than d. So that was all kind of previously known work. The contribution in my paper is to show that whenever we follow this double homological product, we always end up with a code that has this soundness property. So in particular, we have a soundness property where f of x is equal to x cubed, although I think you could probably improve this to x squared. So note that this doesn't depend on the number of qubits. And so if we have any family of classical codes where the code distance grows, we're going to have a quantum code family with good soundness properties. So the proof is going to go in 2 steps. We're going to first look at how we generate what we get after one application of the homological product, and then the second application of the homological product. So an interesting point is that after one step of the homological product, we've got a graph with 3 different types of vertex. And we can think about that as a classical code with no meta checks, but we can also think of it as being, so as a quantum code with no meta checks, but we can also think of it as a classical code with meta checks. So rather than giving you the whole proof, I'm actually going to focus on a sub-lemma. So that the lemma is just that this new classical code that you get at this intermediate stage, which includes codes such as the 2D Ising model, always has a soundness property where f of x is a quadratic function. Okay? So I'll just give you a little sketch of how this bit of the proof works. The kind of extension to the quantum case is kind of similar in spirit, but much more complicated. So hopefully you get a bit of an idea of what's going on from just this case. Okay, so we're applying one round of the homological product onto a classical code, and we're getting what you might think of as a hypergraph classical code. And we can always arrange the bits in 2D. And what the checks are on this new classical code are the following. So you have the checks of the original code applied to every single row here. But then you also apply the checks of a kind of transposed code, where you've just transposed the parity check matrix of the classical code here to every single column. So you know what the checks are on every row and every column of bits. Okay, so the proof proceeds by explicit decoder design. I'm going to give you a decoder that outputs something which has a low weight error, where the weight of the error is bounded by the weight of the syndrome. So let's just say that we've got some error that gives us the syndrome. Okay, and then we're going to try and reduce the error. We're going to try and reduce the weight of the error. Okay, so we look at every row and we look for a code word of the original code, and then we look at every column and we look for a code word of the transposed original code, and we check that they intersect. Okay, so by intersect I mean that there's a bit here which shares the same row and column, and this one is has a 1 on it, has a flip on it. Okay. So what we can show next is that if we kind of take the cross product of these 2 code words, what we find is that the cross of these 2 code words of the original code becomes a code word of the new code that we've constructed. So this is a stabilizer of the new code that we've constructed. It has trivial syndrome. So that means that I can add it to this error on the left-hand side and get something that has the same syndrome as on the left-hand side. But what you can see is that I've reduced the weight But perhaps more importantly, I've completely eliminated this column of errors and this row of errors. And I can repeat this process, and one can show that assuming that the weight of the error wasn't too high, it will eventually terminate in a situation where every single row and column that is left remaining is not a code word of the original classical code. And what this also means is that for every single row and column that you have here, there's actually a check of the new, at least one check of the new classical code that is violated. So the weight of the syndrome in the new code is at least as big, so this is X, the weight of the syndrome is at least as big as the number of columns, which are not code words, and the number of rows. So that tells you a lower bound on the weight of the syndrome, but you also have an upper bound on the size of the error. So the error is inside this patch here, right? It's inside some square that has a size, or some rectangle, which has a size which is equal to the number of columns times the number of rows. So you can just take these two inequalities and rearrange them to get a relationship between the weight of the error and X, which is in fact quadratic. So that's how the proof proceeds, basically, is to go through this decoder and show that assuming that the weight of the error wasn't too large, you're going to have something which has small weight. So this proves the soundness property. So this was really just for this kind of intermediate step where we had applied one round of the homological product. So I want to close with kind of open problem. So I was kind of happy with how this project went as compared against my original goal. So my original goal was to try and conjure up a notion of some kind of code property and analysis of codes and maybe make some new codes such that it included all of the examples that I was already familiar with. And all of the examples that I was already familiar with were topological codes. And in all of these instances, they have this soundness property. So in that sense, I was happy. But then kind of earlier last year, this paper came out, which showed that there's a way of performing, it's a kind of non-topological construction as well, and we'll hear about it later on in the conference, that uses just one application of the hypergraph product, but on the assumption that the classical code that you put in is an expander graph code. Okay, so it's a different construction, but it has single-shot error correction. And for a while, I just thought, well, you know, when I get round to sitting down and analyzing it, I'll find that this code family has good soundness. Until Anthony, just really a couple of months ago, explained to me that, in fact, it doesn't have good soundness, and you can show that it definitely has bad soundness. So what this means is that I'm kind of coming back to this question I posed earlier, that is this sufficient property also a necessary property? Is it a necessary property that you have to have in order to have single-shot error correction? No, it's not, because we have a counterexample. So this kind of leaves open further work, which is to try and come up with a formalism or a necessary and sufficient condition, if you can get both of those, such that you capture all of the examples that we know of, all of the examples that I've talked about today, and also this example here. And as far as I'm aware, that doesn't exist in the literature at the moment. Okay. So that was everything I wanted to tell you today. Thank you for listening.
Thank you all. We've got, yeah.
So I was a little confused about, I think, your second mini result. Yeah. So in the context of the 3D color code, I thought that satisfied all of those conditions, but it doesn't have a high energy barrier, right? It has, I assume it has good soundness because it has single-shot error correction. It has polynomial distance. It has, and it's LDPC.
Yeah. So the third one that was saying that for no 2D topological code.
No, but this was the second result that I was confused about.
Oh. Good soundness plus LDPC entails macroscopic energy barrier.
Yeah.
Yeah, so it only has...
For the 3D color code, how does that...
For the 3D color code, but the 3D color code only has single-shot error correction against one species of error. Yeah. Unless you do the gauge. Unless you do gauge fixing.
But this doesn't apply to subsystem codes? Is that the
No, that's maybe the other thing I should have emphasized. This is not subsystem codes.
Well,
That was. I had two questions. The first one was about subsystem
Yeah.
codes. What could you say about codes? We have local checks, but non-local stabilizer generators. I guess that's open, is what you're saying. The second question I had, in the spirit of the motivation of this, is your construction still leads you to a CSS code at the end of the day because it has X checks and Z checks. What is known, or what can you say about non-CSS codes that might or might not have the one-shot property?
Yeah, so the encodes that I gave were CSS codes, but everything, all of the kind of mini results were valid for any stabilizer code. So it didn't have to be a CSS code. You could have stabilizers that were mixtures of like X, Y, and Z Pauli operators.
Okay, they didn't rely on that homological product, which gives you the CSS. They were more general than that.
Yeah.
Okay.
So the kind of first half of the talk is almost completely general in the sense that it holds for all stabilizer codes and it gives you a sufficient condition for when you can do single shot error correction. And then the second half of the talk, I was just talking about the homological product.
Thank you.
So the advantage of using the single shot construction is that you cannot, you don't need to do D layers of error correction in order to do this. So if you have stochastic noise, then you can do just one layer, and you would get results which would still be, may have some residual errors because it's not adversarial, because you're not limited by the distance, but you have some small errors with, possibly with high probability. So, but what is the advantage? Do you know if there is advantage of, regarding the threshold with this construction?
What the threshold is?
Well, so you have errors that are errors in qubits, there are errors that are errors in measurements, and then you want to see what is the best possible scenario, how do you, to achieve, big fault tolerance in a big system.
Yeah.
So you don't know whether this gives advantage compared to repeated error correction?
So maybe if I just check that I've got the question right, it's that everything that I've been talking about today has been for adversarial noise. But if you want to talk about thresholds, then you have to talk about stochastic noise. Yes. So what hope is there to learn about thresholds from this? Is that what you're... Yeah. So, yeah, I haven't gone near that. I think, this was kind of my first attempt at tipping my toes into single-shot error correction. My conjecture would be that if a code is LDPC and it has good soundness, then it should have a threshold. That's what I would guess. It seems reasonable.
Okay, we're slightly over time. Let's thank Earl again.